is the next American megacity forming right before our eyes. Between Austin and San Antonio lies the I-35 corridor, an 80-mile stretch housing over 5 million residents and experiencing unprecedented sprawl. Today, we're going to break down how we use deep learning to map this convergence and predict its exact future urban landscape for the year 2027. We'll also show why this region may become one of America's most important growth corridors. What happens here could reshape transportation, housing, and economic development across central Texas for decades to come. The problem with predicting urban sprawl is that cities expand faster than infrastructure planning. To solve this, we first need to teach an AI to understand satellite imagery. We start with the Eurosat dataset containing 27,000 tiles across 10 different land use classes. Our goal: to train a backbone model that recognizes these visual patterns so that we can transfer that knowledge to our real-world Texas data. Our pipeline is broken into 4 phases. Phase 1, our dual output backbone. Phase 2 slices massive Google Earth Engine images into manageable chunks. Phase 3 uses a recurrent neural network, LSTM, for temporal forecasting. And finally, Phase 4 decodes those predictions to visualize the 2027 corridor. In short, pixels turn into embeddings, embeddings turn into sequences, and sequences turn into a forecasted map. Each stage builds directly on the outputs of the previous one. Let's dive into Phase 1. We designed a unique dual output backbone based on ResNet 18. In a single forward pass, a satellite tile produces both a 512-dimensional embedding and a 10 class logits. The embedding acts as a compressed summary that will feed our temporal forecasting model later, while the logits allow us to classify the tile's current land use immediately. This gives us both understanding and prediction power.
Training these models yielded impressive results. After just 5 epochs, both our ResNet 18 and a parallel vision transformer model converged rapidly, achieving over a 98.4% validation accuracy. The models effectively learned everything they could from the training data and giving us pretty highly capable feature extractors. So ResNet 18 was plotted in blue and VIT base was plotted in orange. We show the graphs here of cross-entropy loss and validation accuracy. Both models were able to converge in about 5 epochs. Now the next thing we did was kind of run inference on the tiles we got from Eurosat. So the model was pretty confident on industrial and forest tiles, like we kind of show here. What's to note about this diagram is that the color of the border on each tile represents the predicted infrastructure tier, which we'll touch on in the next slide. But the thickness of the border kind of represents the confidence in terms of how confident it was in classifying something. So like we just mentioned, the 10 Eurosat classes mapped to 4 infrastructure tiers. You can see the ones we decided to go with here: high density urban, distributed residential, low load agricultural, and zero load conservation. The idea was that the more red you get, the more urban it is, the more dense it is, the more blue you get, the more pristine it is, the more closer to nature it is. You can see that we mapped the 10 Eurosat classes here to the 4 infrastructure tiers. Now in phase 2, we were slicing the I-35 corridor, so we got a bunch of TIF files. At first we picked the odd ones from 2017 to 2025, but we later added evens as well. In the TIF, we picked out our I-35 corridor, and we looked at 64 by 64 chunks. The idea was we would pass it through a frozen ResNet 18 backbone and then get out a 512 embedding and a B-box, which would give us latitude and longitude. And then we would turn that into PT files, which are basically the embeddings we used for our trainings.
What is an embedding? We don't feed raw image files into our temporal model. Instead, we use our frozen Eurosat trained ResNet 18 as a feature extractor. It takes each 64 by 64 satellite chunk, which is over 12,000 raw pixel values, and pushes it through our network to output a dense 512 dimensional vector. This achieves a massive 24 times data compression, distilling the physical landscape into a strictly mathematical embedding. You can think of these 5 12-dimensional embeddings as the digital DNA of a specific coordinate grid. When we isolate a single patch of land and look at its activation maps over time from 2018 to 2023, you can physically see the mathematical transition. Notice how specific regions of the matrix which our model has learned to associate with an industrial signal progressively brighten year over year as the actual land undergoes development. By passing these embeddings through our classification head, we can map the historical evolution of the entire I-35 corridor. We group the raw land classes into 4 tiers: red for high-density urban, orange for distributed residential, green for agriculture, and blue for conservation. Watching the progression from 2016 to 2020, you can see the red and orange zones rapidly expand, capturing the urban sprawl fusing the cities. To forecast future development, we built a sequence model using PyTorch LSTM. We feed the network a timeline of past embeddings, for example, historical vectors from 2016 through 2025. The LSTM's hidden states carry the memory of the corridor's growth dynamics, allowing for a final fully connected layer to project a brand new embedding for 2027. As shown by our optimization convergence, the model successfully learns these latent trajectories, dropping to a highly accurate mean squared error loss of 0.035. To ensure our model doesn't lose early historical context over these long sequences, we integrated residual skip connections into our architecture, which helps provide mathematical stability to the gradient during training. As we can see from this graph, there was a significant increase in industrial, residential, and highway tiles, and a decrease in crop and forest tiles between 2025 and our predicted 2030.
To build our forecast, we designed this custom LSTM in PyTorch as the model's memory. By feeding it decades of satellite sequences, the LSTM learns to track the velocity of urban sprawl rather than just static land use. The model then projects the internal memory through a final linear layer to predict how the landscape will shift in the next cycle. We train it by comparing these results against the real-world 2025 imagery, ensuring the AI captures the true rhythm of Texas development. If we decode the model's internal predictions back into reality, we can visualize. We can take the 2027 embeddings and pass it through our frozen ResNet classifier head. This generates up to 10 logics, which we can map into 4 distinct infrastructure tiers, ranging from high-density urban to zero-load conservation. And we can see clear development from 2017 to 2027. The expansion is undeniable. But where exactly is this growth happening fastest? To answer this, we calculate the velocity of the growth as measured by a vector shift in magnitude from 2025 to 2027. The heat map reveals the intensity of clustering along the I-35 diagonal. We can pinpoint the growth fronts, such as Southeast Austin, rapidly transitioning from agriculture to industrial use, San Marcos from rural to urban, and the New Braunfels area from conservation to non-conservation. These hotspots are driving the force between our next model's iteration. Some of our key takeaways. Our pipeline used a high-accuracy ResNet model to turn a raw satellite data into a compact 512-dimensional signal, and then LSTM learned of the trajectory of the signals over a decade, allowing us to decode a predictive 2027 land use map. This reveals a physical convergence of the Silicon Prairie, showing Austin and San Antonio merging into a single megathread. Looking forward to 2030, our spatial temporal map captures Urban Globe, a high-density urban artery that will eventually unify Austin and San Antonio into a single economic unit. You can see the life cycle of our master evolution grid, where the bridge between two cities becomes a continuous landscape. But under the hood, we identified some predictive friction, like spatial ghosting, where an elevation-blind model predicts growth in impossible areas. We also hit a resolution ceiling of 64 pixels, which occasionally collapses high-density apartments and single-family homes into a single tier. Finally, we may suffer from stochastic drift, where small errors amplify into blurry latent states. Finally, we want to thank our professor, Constance Carmenis, for teaching us how to put all this together and solving the future of the Silicon Prairie one pixel at a time. Thank you.